Um, I'm gonna get started. So your midterm grades have been posted. They're visible and available. If you don't like your midterm grade and you want to improve it, the best thing you can do is submit work you hadn't submitted, submit late work. You can always do this, even if you're marked as a zero. I mark grades as zeros to calculate the midterm grades, not because I'm not accepting any more work. It's just, I need to mark the not completed stuff to calculate grades. So midterm grades are up. General suggestion, if you don't like the grade you got, do more of the homework and the worksheets and stuff. They're there to help you improve your grade. What else? So the next set of worksheets is due on the 30th. This chapter is 15 through 22. Homework number 3 will also be due on the 30th. And exam number 3 will be on the 30th. And if you failed to meet the active pursuit requirements, you have now been dropped. I think there was only one person who had that issue, so. And I contacted them, so it's not a big deal. That was what the active pursuit was. You have to meet active pursuit or else you get dropped. Which is what I said on the first day. So, let's see, anything else? Make sure you sign in. The next set of worksheets and homeworks is due on the 30th. And the exam is also on the 30th. It will also be 60 questions like the previous ones. And I've gone through and made sure I won't make the same mistake I made on the last one where I accidentally made it out of 75. Changed from the last time I taught this class. So continuing on with our discussion of the life cycle of stars and the birth and death of stars. So we have star birth. We were talking about that life cycle of stars, how stars are born, where you have that collapsing cloud that heats up in the center. Yes. How about your mom? I think it's on my.ccc. I'm not entirely sure. But it's wherever the official roads are. Like I posted it on my.ccc, so my guess is there. You can also use your score on bright space and the curve in the syllabus and the grade segmentation in the syllabus. That'll match up. But, yeah. Yeah. So here is, the continuing video on Starbucks.
As gravity compresses a piece of the cloud, its center heats up because gravitational potential energy is converted into thermal energy. The contraction can continue because the cloud fragment radiates away enough of this energy so that gravity remains stronger than pressure, a process helped by the fact that gravity strengthens as the cloud shrinks in size. The cloud spin also increases as it shrinks because of conservation of angular momentum. The gas becomes hottest and densest at the center of the cloud, making what we call a protostar, while some of the rest forms an orbiting disk in which planets can later form. This process can be quite violent, and protostars sometimes shoot jets of high-speed gas outward along their rotation axes. Gravitational contraction continues to heat the protostar's core during this time, and we say that it is born as a new star when the core becomes hot enough to sustain nuclear fusion of hydrogen into helium. Before we continue, use what you've learned previously about the Sun to answer this question. What happens to the core of a star if its fusion rate is too low to replace the energy it radiates from its surface? Does the core contract and cool down, contract and heat up, or stay the same temperature? The answer is B. The core contracts and heats up, which in turn raises the fusion rate. That is why a protostar's core continues to contract until it comes into energy balance, in which its fusion rate matches the rate at which energy is radiated from its surface. As gravity
So sort of summary of the process of the birth of a star. You have some cloud, gas, and dust. That cloud will start to shrink and fragment. Each of these fragments will continue to collapse. So some sort of event causes the cloud, gas, and dust to become unstable and start to collapse. The gravity will cause this cloud to shrink and fragment. The core of the shrinking cloud fragment will heat up. And when that core gets hot enough, fusion will begin and stop the shrinking. And that is a new star. And that's when the star moves on to the main sequence. And it achieves a long-lasting state of balance. And in this process, it'll develop, in that settling onto the main sequence, it will have strong stellar winds and will push out most of the gas and dust around it and clear its area. And as that cloud collapses, it will form a dense lump in the middle with a disk around it. That disk can form planets. So this star will settle onto the main sequence. The protostar will settle down, the winds and the jets will diminish, the disk will likely form planets, and the stellar wind and radiation pressure that constantly comes out of the star will clear the area around the star, clear out the nebula around the star. But the star and the possible planetary system will remain. And we can observe this happening in several nebulae. We find basically protostars surrounded by dusty disks that we can observe. So as a star evolves, it changes its position on the HR diagram. It becomes, something like one solar mass will come in, settle down. This is where fusion starts. Then it'll bump up and settle onto the main sequence, sort of sequence. This dotted line is the zero-age main sequence. That's where fusion starts. So overall, the surface temperature increases while the luminosity decreases because it gets hotter but also smaller. And the core reaches a critical temperature. Nuclear reactions begin and the star will settle onto the zero-age main sequence. So this turnaround, where it goes from going down to going up, that's when fusion begins. And then it settles onto this dotted line, this line here, the zero-age main sequence. And a brown dwarf is got a mass less than 0.075 solar masses, so less than 7.5%. The nuclear reactions never begin. So you never get a particularly bright star. So here, these are stars settling onto the HR diagram. You can see they have this dip. Fusion begins, they climb up and stabilize. So they evolve, the evolution of stars somewhat more and somewhat less massive than the sun. They're similar paths, but they wind up at different places on the main sequence. If the mass of the fragment is too small, you get brown dwarfs. Here's a couple examples of brown dwarfs. So things like Barnard star. These are, you can see they're quite small. Scale, same scale as Jupiter. They're small and dim. Barnard star is not quite a brown dwarf, but Blues 229 is. The star formation begins as a cool molecular cloud in space. As material collapses down, you get disks and jets formed, and the HR diagram can be used to study these stages of stellar evolution. So we talked about the birth of stars. Let's talk about how massive they are. So this is a brown dwarf orbited by a planet. This is Argus conception in a system with multiple stars. We expect brown dwarfs to look somewhere in between giant orbiting planets and stars. And here's an infrared image showing brown dwarfs circled in the constellation Orion. They're easier to spot in star-forming regions like this because young brown dwarfs still have a lot of thermal energy left from their formation. They're still hot, they haven't cooled down, so they are easier to identify. So they emit measurable amounts of infrared light.
At this point, the protostar has become a newborn, hydrogen-fusing main sequence star. Its precise location along the main sequence depends on its mass, with more massive stars at the upper left and less massive stars at the lower right. Observations show that massive stars are the rarest, and the most massive stars have masses between 100 and 200 times the mass of the Sun. At the other end of the main sequence, low-mass stars are increasingly common, but there is a cutoff at about 8%, or 0.08 times the mass of the Sun. The reason for this cutoff is that something called degeneracy pressure prevents lower-mass objects from contracting to the point at which fusion can bring them into energy balance. Degeneracy pressure arises because the laws of quantum mechanics place limits on how closely subatomic particles can be packed together. We can understand the idea with an analogy in which students try to find seats in a classroom. If there are many more chairs than students, then students can move freely and could be compressed into a smaller space. This is analogous to the situation in most stars, in which degeneracy pressure is not important. However, if the number of chairs becomes similar to the number of students, then the students can no longer be squeezed into a smaller space. This represents the situation with degeneracy pressure, in which quantum mechanical limitations prevent subatomic particles from being further compressed. Notice that this means we must consider two different types of pressure when considering whether gravity can overcome pressure in stars. Thermal pressure is the ordinary pressure that we are used to from our daily lives, and it is characterized by having temperature rise as pressure increases. This is the pressure that balances gravity in normal stars. In contrast, degeneracy pressure does not depend on temperature. As a result, an object in which contraction has been stopped by degeneracy pressure can remain at the same size indefinitely, even as the object cools with time. It is degeneracy pressure that stops the collapse of protostars with masses less than 0.08 times that of the Sun, leaving them as the not-quite stars that we call brown dwarfs. Brown dwarfs are very common, but are difficult to detect because they are so dim. The circles in this image represent locations of brown dwarfs detected in the Orion Nebula. In coming chapters, we'll see that degeneracy pressure can also come into play much later in stellar lives, and in particular when stars exhaust all their fuel for nuclear fusion. To recap,
So degeneracy pressure is very important in the deaths of stars, which is what we'll be covering in the next chapter, which we're getting to pretty soon. But it's also important, there's sort of this minimum compression you can achieve, which is why stars below 408 solar masses, they're held up by, they never get hot enough. They get stopped by degeneracy pressure before they can compress enough to get hot enough for fusion to start. So you can get a cluster with lots of stars forming from a single cloud, and this actually is one of the best ways we have. This leads to some of the best ways we have to study the evolution of stars, because there's all these clusters that all formed around the same time, but of stars of different masses and such. So we can study how, each cluster is the same age, so we can study how stars vary with age by looking at different clusters. Very massive stars are rare, low mass stars are quite common. So you get this distribution with very few large stars and lots of little stars. And there's an upper limit on the mass of the stars. So the lower limit is set by degeneracy pressure. There's a point where you can't compress the star anymore, so you never get hot enough for fusion to begin. There's also an upper limit. The upper limit is set by radiation pressure. So light, when it hits something, actually pushes it a little bit. So photons exert a very slight amount of pressure when they strike matter. And very massive stars are so luminous that the collective pressure of the photons drives their matter into space. So if you get big enough and pump it out so much light, you could have enough light pushing out that you'll actually push off the outer layers of the star, and they'll be lost. And that sets a maximum size for stars. And models of stars suggest that radiation pressure limits how massive a star can be without blowing itself apart. Observations haven't really found stars more massive than about 120 solar masses, and the theoretical limit is about 300 times the solar mass of the sun. 300 times the mass of the sun. And fusion won't begin in a contracting cloud if some sort of force stops contraction before the core temperature goes above 10 million Kelvin. The core has to get to 10 million Kelvin. So if something else stops the compression, which stops the heating, it'll never start fusion. So thermal pressure can't stop contraction because the star is constantly losing thermal energy from its surface through radiation. So it can't be stopped by the heat of the star unless there's something generating heat, because it's constantly radiating off heat. So it will keep collapsing. But there is another form of pressure that can stop the contraction. And this is degeneracy pressure, which is due to the Pauli exclusion principle of quantum mechanics. So certain types of particles are what are called fermions, named after Enrico Fermi. And they have this property that you can't have two fermions doing the same thing in the same place, basically. They will not copy each other. You cannot have perfect duplicates of fermions. And some examples of fermions are electrons, protons, neutrons. Most of the stuff that makes you up are fermions. It's a specific thing that has to do with the spin of the particles. If they have a spin that is halfway in between a whole number, so electrons have spin 1/2, so do protons as well as neutrons. Those are all fermions. If they have a spin 1 or 2 or an integer value, then they'll be what is called bosons. Bosons can copy each other, and they're totally happy about that. But so the relevant source of this degeneracy pressure in stars is electrons. So the laws of quantum mechanics prohibit two electrons from occupying the same state in the same space. And this means, and the states in question are energy levels. So they correspond to how these electrons are moving. So you get to a point where you cannot compress a star anymore because the electrons would have to move too fast. because every time you make a star smaller, you basically reduce the number of states it has at the energy levels. So you get more electrons piled up in higher states. So there's two types of pressure. There's thermal pressure and degeneracy pressure. Thermal pressure depends on heat content. The main form of pressure in most stars. The hotter you get, the more pressure there is. Degeneracy pressure says particles can't be in the same state in the same place. This does not depend on heat content. It's entirely a quantum mechanical effect. It has to do with, fermions are not allowed to be degenerate. You're not allowed to have two fermions in the exact same state. I mean, they can be degenerate for one version of it, but that's the idea. It has to do with the filling of these states. And the example of a room with a limited number of chairs. So the idea is that as you make the room smaller, there are fewer chairs, and eventually you're going to have a problem. So degeneracy pressure will halt the contraction of objects with masses less than 8% of the mass of the sun before their contraction can heat them up enough to start fusion. So star-like objects that are not massive enough to start hydrogen fusion are brown dwarfs. They do get hot, they get hot enough to start deuterium fusion, but deuterium fusion on its own just isn't good enough. And so a brown dwarf will emit infrared light because of the heat left over from its contraction, and its luminosity will gradually decline with time as it loses thermal energy. Because they're not really generating any energy or any significant amount of energy. They start out hotter, they cool down slowly. And infrared observations can reveal recently formed brown dwarfs relatively easily because they're still pretty warm and luminous, because they just collapse, so they're still hot from that process. They haven't cooled down from formation, but they never got hot enough to start fusion, so they're just going to cool down. So stars more massive than about 300 times the mass of the sun will blow apart. Stars less massive than 0.08 times the mass of the sun can't sustain fusion. And in fact, with more modern stars with more heavy elements in them, that limit for blowing apart is lower than 300 solar masses. It's more like 120, 150. 300 solar masses is what we would expect to see with a star that is only hydrogen and helium. So interstellar medium is made out of gas and dust. Emission nebulae are hot glowing gas associated with the formation of large stars. Dark dust clouds, especially molecular clouds, are very cold, and they can be the seed for the beginnings of star formation. Dark clouds can be studied using the 21 centimeter emission line of molecular hydrogen. And star formation begins with fragmenting, collapsing clouds of dust and gas. And a cloud fragment collapses due to its own gravity, and its temperature and luminosity will increase. And when the core is sufficiently hot, fusion will begin, and a star is born. Collapsing cloud fragments and protostars have been observed. We can see them in various nebulae. Mass determines where a star will fall on the main sequence, and one cloud will typically form many stars as a star cluster, because it'll fragment, and each of the fragments will form a star. So that's the end of chapter 20 and 21, and now we're going to go on to 21 and 22, basically. That was interstellar medium, star birth. We talked about the birth of stars. Now we're going to talk about what happens at the ends of stars' lives. Let me share. I hate that bug. That seems to be the only way to fix it. So we talked about how stars are born. Now we'll talk about how they evolve, how they go through the life cycle, basically. So how can we understand the life of the star? So the time scales of a star's lifespan are just too long. Even the shortest of stars live millions of years. Generally live on the order of millions of years. So we can never watch a star go through all its life stages, because lifespans of stars are on the order of millions to billions of years. So how can we understand how humans change over their lifetimes? We can't easily observe humans throughout the entire lifetime, or at least not in a short time scale. So you imagine the idea of if you had a project, it's like a semester project, to study human aging. You can't follow one person through their life cycle of all their stages of their life. Let's just see. But you can study groups of people at various ages, like infants, children, adolescents, young adults, middle-aged, elderly, etc. And if you put this together, you can understand how humans age their lives by looking at groups of humans of various ages. We can do the same things studying stars. Because stars are all born in groups and clusters, we have clusters of stars that are all the same age. So if we look at different clusters, we can see how stars evolve through time as they age, because each cluster will be a different age. So star clusters act as laboratories to study stellar evolution. Because star clusters are groups of stars that form essentially at essentially the same time from essentially the same material. They really only differ in mass. So they are effectively a controlled experiment. Which is good because we can't make stars in the lab. And this allows us to study the effects of mass on the evolution of stars. Different mass stars will be at different stages of evolution within the cluster. So we can see how, this cluster is so old, we can see how that affects different mass stars. And by comparing many clusters, we can start to figure out the process of evolution that stars go through. So there's two main types of star clusters. In our galaxy, there are globular clusters, which are located in the outer spherical region of our galaxy. They are the halo. They're very large. They consist of like 100,000 stars. And they're typically very old, billions of years old. In fact, there are some that are on the order of like 13 billion years old. Like as old, almost as old as the universe. And then there are open clusters. These are located in the disk of the galaxy. These consist of around 1,000 stars usually, and they're often quite a bit younger, less than 100 million years old. And there are, of course, clusters in between, but these are two common types. We have very old clusters and much younger clusters. So this is a globular cluster. This is an open cluster. There are also OB associations. These are groups of hot young stars that form together in a small region of space. Because they're these big, massive stars, they must have formed quite recently. And they also contain many smaller stars, often still in the process of forming. So these are sort of the youngest of clusters. They are found associated with gas and dust, these star-forming regions. These are star clusters that have just formed or sort of in the process of forming. So very young, very hot stars, because you still have the big ones left. And often many smaller stars, often still in the process of forming. And these are in the star forming regions. So we can compare models with the actual star clusters. We can make models about how we think stars evolve, what we would expect to see in star clusters of certain ages, and we can compare them to actual clusters. So here, if you have a young cluster that's maybe a few million years old, some stars will not even have reached the main sequence yet. They're still forming. Next, we have something like 100 million year old cluster. Where things have more settled onto the main sequence. So here we're looking at some clusters of various ages. This is a very young cluster. Stars have already started fusing here. Some are still moving on to the main sequence. A little bit later, something like 10 million years. I think that's a typo. Some stars have started to leave the main sequence and die. The most massive stars have already left the main sequence after 10 million years, whereas some of the least massive haven't even reached it yet. So here we have something like a 4 billion year old cluster. You can see lots of stars have left it. And here's a 10 billion year. That's a 4 billion. So this is a 100 million year old cluster. This is a 4 billion year old cluster. And we'll get to the 10 billion. So here's after about 100 million years, you get a distinct main sequence turnoff begins to develop. This shows you the highest mass stars that are left on the main sequence. And after a billion years, the main sequence turnoff is a lot clearer. And you have many red giant stars around it. And here is the 10 billion year old cluster. As you have this very sharp turnoff, we can see these stars sort of evolving. And the turnoff point lets us figure out how old the cluster is. So after about 10 billion years, we get a number of additional features. We have the subgiant branch, we have the red giant branch, we have the asymptotic giant branch, and we have what's called the horizontal branch, and a bunch of white dwarfs down here. So this is what we see in globular clusters. So the red giant, subgiant, asymptotic giant, and horizontal branches are all clearly populated, and white dwarfs indicating that solar mass stars in their last phases also start to appear. So the youngest cluster need to be 1 million years old or less. Stars we see in them won't live any longer than this, and the oldest globular clusters are more than 11 billion years old. These are some of the earliest stars to form in the universe, and they help us estimate the age of the universe. They give us sort of a lower limit on our age. You know, the universe must be older than these old clusters. So here we have this double cluster, H and Chi Persei, must be quite young. Its HR diagram is of a newborn cluster. It can't be more than about 10 million years old. So there's stars that are still sort of settling onto the main sequence. The turnoff is very high. There's only a few red giants. Here, the Hyades cluster is also rather young. Its turnoff indicates an age of around 600 million years. So here, we do have a clear turnoff. We do have some red giants. We have some white dwarfs from the death of some smaller stars. So it turns out you don't get white dwarfs from the biggest stars. You need to have it be, well, I think the limit, the cutoff is around 8 to 10 times the mass of the sun. Then there's the transition. And this is M80. It's a globular cluster. It's something like 10 to 12 billion years old. Much older than the previous examples. And you can see there's this, you can see this whole structure where there's the turnoff, then there's the subgiant branch, the red giant branch, the asymptotic giant branch, the horizontal branch, the white dwarfs, and these stragglers. So we can understand stellar evolution by looking at stars in various stages of their evolution. Star clusters provide good laboratories for studying stellar evolution because the stars in them formed at the same time and from the same material. And the oldest clusters help us get estimates of the age of the universe. So let's talk about a star when it leaves the main sequence. We talked about how the star entered the main sequence. We previously talked about what stars do on the main sequence, which is sit there and fuse hydrogen into helium. Not much is what stars do on the main sequence. They don't change much. But eventually, they run out of hydrogen in their core, and they will evolve off the main sequence. So we'll start with the life stages of a lower mass star. So you start, with a protostar, you settle on to yellow, lower mass. This is a lower mass star down here. This is a high mass star up here. For a lower mass star, you start with a protostar, you settle onto the main sequence. Eventually, you run out of fuel. The core collapses, gets hotter. Fusion starts in a layer around the core, and that pushes out the outer layers. And you get a red giant. Then you can stabilize the core. When helium starts to fuse, it will shrink a little. And then the helium will run out, and you can get this double shell fusion thing, where it's another stage of red giantness, and eventually it'll blow off its outer layers in a planetary nebula and leave behind the core as a white dwarf. We'll go all through all this in detail. So life on the main sequence is the boring part of the lifespan of a star. About 90% of a star's life is spent on the main sequence. Not much will change for millions, billions, or even a trillion years, depending on the mass of the star. It will continue to convert hydrogen to helium through nuclear fusion. This will only occur in the core. The outer layers will remain unchanged. The core will become depleted in hydrogen and enriched in helium. It's less hydrogen, more helium. And the core's temperature will slowly increase. This will increase the fusion rate. And the luminosity as the star goes through its lifespan. So it'll remain on the main sequence as long as it can fuse hydrogen into helium. But eventually, it's going to run out. So while it's on the main sequence, gravity and thermal pressure balance. The star remains in equilibrium. If the fusion rate decreases, the core will collapse again, increasing the fusion rate. If the fusion rate increases, the core will expand a bit, decreasing the fusion rate. And so gravity and thermal pressure will be balanced. So how long does a star live? It depends on the initial mass. Larger stars have more mass, but they go through it at a much faster rate. So they can use up their fuel in the core in 1 million years, while smaller stars have less fuel, but they consume it more slowly. So therefore, fuel could last as long as 1 trillion years. So like an O5, with a surface temperature of 54,000 Kelvin, about 40 times the mass of the sun, has a lifespan of around 1 million years. A B0, with a surface temperature of 29,200, 16 times the mass of the sun, about 10 million years. A0 at 9,600 Kelvin, about 3.3 times the mass of the sun, 500 million years. F0 at 7350 Kelvin, 1.7 times the mass of the sun, 2.7 billion years. G0, just a bit larger than the sun, at 6,050 Kelvin, about 1.1 times the mass of the sun, about 9 billion years. Sun's a little smaller, its lifespan is around 10 billion. K0 at 5240, 0.8 times the mass of the sun, about 14 billion years. And M0 at 3750 Kelvin, 0.4 times the mass of the sun, 200 billion years. And there are, of course, even smaller stars. So eventually the hydrogen in the core of the star gets consumed, the star begins to leave the main sequence. And its evolution depends very much on the mass of the star. The low mass stars go relatively quietly, the lowest mass stars are the most quiet, and high mass stars go out with a bang, quite literally. So let's start by talking about the life stages of a low mass star, like the sun. The lowest mass stars just peter out, but yeah.
This two-part set of narrated figures summarizes the life stages of a low-mass star like our Sun. You may find it helpful to review the narrated figures on the solar thermostat and the HR diagram before you begin. This figure shows the life track, also called an evolutionary track, for a one solar mass star on an HR diagram, along with a set of diagrams that show what is going on in the star's core at 3 stages near the end of its life. The figure may look complex, but its fundamental message is simple. The characteristics we observe for stars at different stages of life reflect the way nuclear fusion occurs in their cores. Let's begin by looking at the HR diagram. The annotated life track shows how the observable properties of a low-mass star like the Sun change in its final stages of life. Each point along the track represents the star's surface temperature and luminosity at a particular time. The track begins at the point representing the star's surface temperature and luminosity during its main sequence life, when it generates energy by fusing hydrogen into helium in its core. To help you understand the changes that occur later in the star's life, let's first review how our star became a star. Recall that a star begins its life as a clump of gas that contracts because the inward pull of gravity is stronger than the thermal pressure that resists it. This process of gravitational contraction heats the cloud because some of the gravitational potential energy it loses is converted into thermal energy as it shrinks. The center of the cloud heats up and begins to shine as a protostar, with its contraction continuing until its core becomes hot enough for nuclear fusion of hydrogen into helium. Now consider this question. What else happens to the cloud as it shrinks? Does it begin to emit X-rays? Do its materials separate by density? Does it spin faster and flatten into a disk? Or does it become more perfectly spherical in shape? The answer is C. The cloud's angular momentum must be conserved, and this ensures that it rotates faster as it shrinks in size. It also flattens out in this process because of the way particles average out their velocities when they collide. Planets can form in these spinning disks, and the fact that planetary systems are found around many or most stars tells us that planet formation often accompanies star formation. However, for this video, we will focus our attention on the forming star at the center of the disk. We can represent the forming star's changes in appearance on an HR diagram. At first, the cloud is cool and dim, so it starts far below and to the right of the main sequence. The cloud becomes hotter and brighter as it contracts, so the point representing it on the HR diagram moves left and upward, and then down toward the main sequence. The protostar remains out of energy balance throughout this process because its core is not yet hot enough for nuclear fusion to replace the energy the protostar is radiating from its surface. The contraction stops and energy balance is achieved only when the core temperature finally reaches the point at which nuclear fusion generates enough energy to match the energy radiated into space. This event marks the star's birth as a main sequence star. For a one solar mass star like our Sun, the formation process takes about 30 million years, and it then spends about 10 billion years as a main sequence star, generating energy through hydrogen fusion in its core. Recall that more massive stars, which are found higher on the main sequence, have shorter lifetimes, while less massive stars have longer lifetimes. The star's luminosity remains quite stable during its main sequence life, thanks to the combination of energy balance and gravitational equilibrium that create the self-regulating solar thermostat, which is discussed in a separate narrated figure. The only significant change during this period is a very gradual brightening as the star ages, which arises from a gradual contraction of the core as hydrogen is converted to helium. Bigger changes begin when the core finally exhausts its hydrogen, but we'll discuss these changes in part 2 of this narrated figure.
So even while it's on the main sequence, the composition of the star's core will change. It's steadily using up hydrogen and enriching the core with helium. So as time goes on, it'll go from about 10% helium by particle count to be more in the core. We see more and more helium and less hydrogen. And eventually, after about 10 billion years, most of the star is still made of hydrogen, but the core is out of helium. It's out of hydrogen and is mostly helium. And so fusion stops working. So our observations of color clusters show that the stars become larger, brighter, and more luminous after their time on the main sequence is over. So when the core of a star runs out of fuel, it collapses and gets hot. This heats up the layers above it and causes the whole star to expand and the outer layers cool. But it actually starts fusion in layers above it, which causes the whole star to get more luminous. So the hydrogen gets consumed in the core, so the star has to change. It cannot continue to burn hydrogen in the core because it has run out. So the core will begin to contract and heat up. And as it gets hotter, it's going to heat the layer of hydrogen above it. And eventually that layer will get hot enough for hydrogen fusion to begin. So hydrogen will begin to fuse in a shell around the core, and the outer layers of the star will begin to expand, forming a red giant. So the core contracts, hydrogen begins to fuse outside the core, because the core is full of this non-burning helium ash. It's not hot enough to fuse. It's just sitting there, more or less. And then the outer layers, but there's a layer of hydrogen above the core that gets heated by that collapsing core that starts to fuse. And that causes the whole star to have a lot more energy being pumped out in it. And the whole thing expands and the outermost layers get cool. So as the core contracts, the shell starts fusing around the helium around the core. The luminosity of the star will increase because the thermostat of the core is broken. The normal mechanism that would balance the star's thermostat doesn't work because increasing fusion rate in the shell doesn't stop the core from contracting and heating more. So this inert helium core that's going to keep contracting until it hits degeneracy pressure. And the shell above it warms up. And so what do we actually see? We watch it get larger and cooler. The luminosity increases and the temperature decreases. So the position on the HR diagram changes. It's producing more energy, that's why the luminosity increases, but it's doing so in an unstable manner, so the whole star gets blown up like a balloon. And because of that expansion, the outermost layers of the star cool off. So the star will move off the main sequence and become a red giant star. So these are some of the stages of a star leaving the main sequence. It'll be a main sequence star, then a subgiant, then a red giant until you hit the helium flash, which is the point where helium starts to fuse. Then it will go on to the horizontal branch. It can then become another red giant, and then it can leave behind a carbon core. And that carbon core becomes a white dwarf, which will eventually cool to become a black dwarf, and the outer layers get blown off as a planetary nebula. So the red giant branch is where the core continues to shrink. The outer layers of the star will expand and cool. So it's now a red giant, and it'll extend out as far at least as the orbit of Mercury. We're not exactly sure how big a star like our sun would get. There's some debate, but it looks like it would be more than that. It would eventually get big enough. There's some debate whether or not it will actually get far enough to engulf the Earth. It will definitely engulf Venus. So despite its cooler temperature, its luminosity increases enormously due to its large size. So the outer layers are cooler, but the whole star is pumping out more energy. So this is the red giant stage on the HR diagram. We step up to become a red giant. So stars will spend the vast majority of their lives fusing hydrogen into helium on the main sequence. When the hydrogen gets used up, the core will contract and the outer layers of the star will expand. The star will become a red giant, many times larger than it was before. So the sun will probably expand to be about the orbit of Venus. Beyond the orbit of Venus. It might get as far as Earth. So the core of a red giant, the core that exhausted all its hydrogen, its core is contracted. So the temperatures in the core will continue to increase. Eventually, the core will get hot enough that helium can fuse. But the temperature required to fuse helium is 100 million degrees. It's 10 times the temperature required to fuse hydrogen. And that's because the process for fusing helium is called the triple alpha process. 3 helium nuclei fuse into 1 carbon nucleus. So a helium nucleus is called an alpha particle, which is why it's called the triple alpha process. So why do you not just have 2 helium nuclei becoming a boron? Or is it boron? Not boron. Related. And the reason is it turns out that it's not actually a stable process for 2 helium nuclei to fuse. There's an issue with the stability of nuclei. You can't actually form. What is the fourth element? Beryllium, that's it. You can't actually form beryllium directly from 2 helium nuclei. It just doesn't work. There's sort of resonance and instability. So it needs to be 3, which is much harder. And how this begins will depend on the mass of the star. For a low mass star, it'll undergo a rapid process called the helium flash, where we'll actually see the star suddenly brighten as helium fusion starts. This helium flash is where all the helium starts fusing kind of all at once. In a high mass star, the beginning of helium fusion starts more gradually. So this process starts more gradually in a high mass star because it's just bigger and hotter in general. So helium fusion doesn't begin right away because it requires higher temperature than hydrogen fusion. This larger charge leads to greater repulsion. And also the fusion of 2 helium nuclei doesn't work. Why is a bit complicated, but in this case, so helium fusion must combine 3 helium nuclei to make carbon. I'm not going to go into nuclear physics to explain why 2 helium fusion doesn't work, but it doesn't. Now, the thermostat is broken in a low mass red giant because degeneracy pressure will support the core. But once helium fusion begins, the temperature of the core will rise rapidly, and so the helium fusion will skyrocket until thermal pressure takes over and expands the core. In a larger mass star, the core is bigger, so it can collapse more before degeneracy pressure kicks in, and get hotter before degeneracy pressure kicks in, and thus helium fusion will start more gradually. So once the core temperature has risen to 100 million Kelvin, the helium in the core will start to fuse. Helium will begin to fuse extremely rapidly within hours. The enormous energy output is over, and the star once again will reach equilibrium. So now, after the sudden burst of helium fusion, now it has active fusion in its core, the thermostat will work again. So the core can expand, but now it's using helium instead of hydrogen. So helium fusion core fusion stars will either shrink or grow because the core's thermostat is temporarily fixed. But it's going to chew through its helium in the core even faster than it consumed its hydrogen. So it won't actually stay in a state that long. After the helium flash, the star will actually contract and warm up. It will become hotter and fainter. It will move down and to the left on the HR diagram. It settles on what's called the horizontal branch, where it's burning helium to carbon in the core and burning hydrogen to helium in the shell. So this is for a lower mass star. Lower mass star, more or less going to stop at carbon. For higher mass stars, which we'll get to a bit later, this process can continue. You can build up carbon in the core, eventually fuse carbon, and you get a series of shells of fusion. And as you go in, you get heavier and heavier elements until you reach the ultimate limit, which is iron. So here you hit your horizontal branch, where you have this stable helium fusion, and it'll stay there for a while. And then eventually, so you start to build a carbon oxygen. Shortly before this, you have a carbon oxygen core produced from helium fusion. You have a layer of helium fusion above that, a helium core above that, a layer of hydrogen fusion above that, and then there's the regular hydrogen of the star. So models show the red giant should shrink and become less luminous after helium fusion begins in the core. And observations of star clusters agree with these models. Helium core fusion stars are found in what is called the horizontal branch of the HR diagram. Eventually, the star will build up a core of carbon. So yeah, the helium is fusing into carbon. That carbon is going to settle in the core. Anything less than 2 solar masses will never get hot enough to fuse carbon. The core will continue to contract and heat up. The outer layers will continue to expand, and it will become a red giant or a supergiant, and will follow what is called the asymptotic giant branch up here. So it'll get very luminous, and it will continue to expand and cool, and eventually it'll blow off its outer layers and leave behind its hot core as a white dwarf. So after the core's helium fusion stops, helium will fuse into carbon in a shell around the carbon core, and hydrogen will fuse to helium in a shell around the helium layer. You have what's called double shell fusion. This double shell fusion stage never reaches equilibrium. The fusion project says fusion rate will periodically spike upwards in a series of thermal pulses. In which each spike, convection will dredge carbon out from the core and transport it to the surface. So it'll go back to the giant branch. It'll become settle. It will go onto the asymptotic giant branch. So as the helium in the core fuses to carbon and oxygen, the core will become hotter and hotter. The helium will burn faster and faster. The star is now similar to its condition just before it left the main sequence, except now there are two shells. There's a core of carbon, a helium burning shell above that, hydrogen burning shell above that. And it's become a red giant for the second time, and will enter the asymptotic giant branch. So for a sun-like star, 90% of its life will be on the main sequence. That's about 10 billion years. The red giant helium-fused part of its life is about 10% of its star's life. It's about 1.5 billion years. Then the second red giant phase is only millions of years. It's much shorter. So the stages get steadily shorter as you go on. So let's talk about those life stages after.
In part 1 of this narrated figure, we discussed the life track of a low-mass star like our Sun up to the end of its main sequence life. We now continue from that point. This diagram shows the star at the end of its main sequence life when it has exhausted the hydrogen supply in its central core. The core is now made mostly of helium, and we say that it is inert because it is not yet hot enough for helium to fuse into carbon. However, the hot gas surrounding the core still contains hydrogen that has not yet undergone fusion. At this time, the inert core is again out of energy balance, as it was before hydrogen fusion began. Gravitational contraction of the core therefore resumes, causing its temperature to rise. As a result, a shell of hydrogen surrounding the core becomes hot enough for fusion, and ongoing core contraction causes the shell to shrink in heat, driving its fusion rate higher. The shell becomes so hot that hydrogen shell fusion proceeds at a much higher rate than core fusion on the main sequence, causing the star's luminosity to rise as its surface expands outward. Contraction of the inert helium core continues over a period lasting about 10% of the star's main sequence lifetime, or 1 billion years for a star with the mass of the Sun. On the HR diagram, the track representing the star's growing luminosity progresses up and right from the main sequence, and its growing size makes it first what we call a subgiant and then a red giant. Keep in mind that the core, shown to the right, continues to shrink even as the star itself grows in size. The expansion comes to an end when gravitational contraction finally makes the core hot enough to fuse its helium into carbon. For low-mass stars, the onset of helium fusion floods the core with thermal energy in an event we call a helium flash. This event causes the core to expand somewhat, but also brings the star back into energy balance, now with a helium-fusing core and a surrounding shell of hydrogen fusion. The core expansion lowers the shell's temperature and fusion rate enough that the star's total energy production falls, even though it now has core helium fusion in addition to hydrogen shell fusion. The point representing the helium-fusing star shifts down and left on the HR diagram, reflecting the fact that the star is now smaller and lower in luminosity than it was as a red giant. With energy balance and gravitational equilibrium restored, the helium core fusion star will remain stable until its helium runs out, which takes about 100 million years for a one solar mass star. Now consider this question. What will happen to the core after all its helium has fused into carbon? Will the core contract and heat, contract and cool, expand and heat, or expand and cool? The answer is A. The core, now made of the inert carbon produced by helium fusion, will again be out of energy balance. It will therefore begin to contract and heat once again, just as it did during the protostar and red giant stages. This time, it will be surrounded by two shells in which fusion can continue. A helium fusion shell just outside the carbon core, and a hydrogen fusion shell around that. Both shells become hotter as the core contracts, causing their fusion rates to rise. The double shell fusion star therefore begins a second red giant stage, in which it will reach an even greater size and luminosity than it did during its first red giant stage. The furious rates of fusion in the shells cannot last for more than a few million years, and the cores of low-mass stars like the Sun never become hot enough for steady fusion of carbon. Meanwhile, the huge size of the dying star will give it only a very weak gravitational grip on its outer layers. The star ultimately expels its outer layers into space, where they glow for a few tens of thousands of years as a planetary nebula. The stellar core that is left behind is what we call a white dwarf. On the HR diagram, we show the transition from red giant to white dwarf with a dashed curve. With no fusion to supply energy, the white dwarf will become cooler and less luminous with time. You might wonder how we can be confident that the life stages of a star really unfold in this way when we have never observed an individual star go through all of them. The answer is that our theoretical models of stellar lives agree with the patterns of stellar properties we observe in star clusters. This HR diagram shows the stars of a single globular cluster, which means the stars are all about the same age. The lowest mass stars have the longest lifetimes, so they are still on the main sequence. Stars of slightly greater mass have already progressed to the subgiant and red giant stages. We see even more massive stars in the helium core fusion stage, and some have already gone through the planetary nebula stage and are now white dwarfs. To summarize, a star's external appearance changes at different stages of its life because of changes in the way nuclear fusion occurs in its core. Before its birth, the star is a protostar in which its core contracts because it is out of energy balance. When the core becomes hot enough for hydrogen fusion, the star enters its long main sequence stage, in which energy balance keeps it shining steadily. After the core hydrogen is gone, the core goes out of energy balance and contracts, leading to the subgiant and red giant stages. When the core becomes hot enough for helium fusion, energy balance is restored, and the star becomes steady again. The star falls back out of energy balance and expands again when the core helium is gone. This marks the end of the line for low-mass stars, because their cores never become hot enough for any other type of fusion to restore energy balance.
Well, let's talk about how a low-mass star finally dies. What happens is that at that double cell fusion stage, the carbon gets bigger and bigger, and eventually it basically just blows off its outer layers as a planetary nebula. It loses a lot of material in that process, but the final death will be the core is just this core of carbon left behind, and the outer layers get blown off as a planetary nebula. So this is the entire evolution of a sun-like star. Starts as a protostar, goes on main sequence, goes through its death, blows off its outer layers, leaves behind a white dwarf, which slowly cools. So such stars, they never become hot enough for fusion beyond oxygen to take place. So double cell fusion ends with a pulse that will eject the hydrogen and helium into space as a planetary nebula. The carbon core left behind becomes a white dwarf. So this is the helix nebula. There's a central white dot. That is the hot white dwarf. And it's the core, this core is incredibly hot. And it's just a ball of carbon held up by degeneracy pressure. So it starts out incredibly hot because it was the core of the star. It was over, it was fusing helium into carbon. So we're talking over 100 million degrees Kelvin. And it collapsed them, so we need to heat it up some more. And then it's just being held up by degeneracy pressure. So it's just going to sit there as the ball, slowly radiate away its heat, and slowly cool. And so it's a white dwarf, and it eventually will become what's called a black dwarf. But to the best of our knowledge, there are no black dwarfs in the universe yet, because the universe is not old enough. Because the process by which a white dwarf cools to become a black dwarf is incredibly slow. So here are some other planetary, this is another planetary nebula. This is the butterfly nebula. The hot white dwarf is hidden in the dark ring of dust in the center here. This didn't blow up, such a nice circular structure, but they make very pretty nebulas. This is, the remains of a star being blown up. So stars become very large because the outer layers are further from the core. The escape velocity becomes lower because the gravitational force becomes weaker. The outer layers are just not held on as strongly. And eventually the outer layers just get expelled out oops, into space and become this planetary nebula. This leaves behind the hot core as a white dwarf. So there's no more outward fusion pressure being generated in the core, which will continue to contract, and the outer layers of the star will continue to expand, forming a planetary nebula. Here are some examples. And they're called planetary nebulas because they were round and fuzzy and reminded people of certain planetary systems or planets. Because they're often ring shaped. But here are some examples. And planetary nebulas are quite short-lived because they're just the outer layers being blown off. They only last a few tens of hundreds of thousands of years. So the star now has two parts: a small, extremely dense carbon core, and this envelope of gas flying outwards about the size of our solar system. The envelope is called the planetary nebula, even though it has nothing to do with planets. Early astronomers viewing this fuzzy envelope thought it resembled a planetary system. And planetary nebulas are not all like round. They have various shapes. So why there's such variation? Lots of stars are in binary systems. So the gravity of nearby stars. Oh, we are out of time. Sorry. I forgot to check the time. We will. Okay. We'll continue on from here next time. We'll see you all on Thursday. Sorry about not noticing the time ran out. Ugh. Are you asking about the question about the slides? Is that the slide? You mean the slides for the project? Like at the end of this semester when you're going to do the presentation, there's a due date on Brightspace. Let's see. So semester project presentation is where you'll submit it. December 5th is when they're due. I'm going to stop sharing.